Now let's take a look at an example of a linear spring problem. Initially, a piston cylinder device contains steam at 200 kilopascal, 200 degrees C, and 0.5 meter cube. At this point, a linear spring is touching the piston but exerts no force on it. Heat is now slowly transferred to the steam, causing the pressure and volume to rise to 500 kilopascal and zero point 0.6 meter cube respectively. Determine the final temperature, the work done by the steam, and total heat transferred. We follow the same four-step process as identified in class. Identify the system, process, substance, fill the table, determine work, and apply the corresponding first law. Step 1. We know the system is closed, so mass remains constant. The substance given in the problem is water, and the process is a linear spring process, which implies that there will be boundary work. Step 2. Filling the table with the givens first. We have pressure and temperature and volume given for the initial state, pressure and volume given for state 2. Next, since there are two intensive properties given for state 1, we can find all of the missing properties. For state 2, pressure and volume are given. Since the system is closed, mass will remain the same. Now we have the volume and the mass for state 2. We can then find the specific volume 2, which is 1.296 meter cube per kilogram. Once found, there are now two intensive properties, here and here. For state 2, we can now fill the rest of the blanks. Phase turns out to be superheated vapor, and we can approximate the temperature and internal energy by eyeballing from the table. And the final temperature is about 1150 C, and the internal energy is about 4350 kilojoule per kilogram. We're now ready to find work. Since there are no electrical resistance nor paddle wheel within this control volume, electrical and paddle wheel work are both equal to 0. The only work for the system is boundary work. We can find the boundary work by finding the area under the PV curve. P and V for the initial and the final state can be found from the table. For the initial state, and the final state, the volume and pressures, like I said, can be found from the table. Since this is a linear spring process, the PV curve is going to look like a straight line. Boundary work can be found from area under the PV curve, which is this rectangle or trapezoidal area under it. We then find the area under the curve by finding the area of the trapezoid. The two bases of the trapezoid and its height. The boundary work turned out to be 35 kilojoules, which is also the total work. We now have everything we need to apply the first law. Boundary work was found on the prior slide to be 35. Mass and internal energies can be found from the table. The total heat transfer rate turned out to be, or actually the total heat transfer turned out to be 819.6 kilojoule. And here are the final answers for the problem. Now, what happens if there's a part D and you are asked to find the amount of work done by spring only? Let's go ahead and sketch the PV diagram again. State 1, let's change color a bit. State 2, connected by a straight line. This case, however, if you look at total work like what we said, total work is this entire area under the PV diagram. We can separate this into two portions. The rectangular portion and let's use green, the triangular portion. The rectangular portion represents work done by the piston, and the triangular portion represents the work done by the spring. Therefore, if you're asked to find the work done by the spring only, you only worry about this triangular portion here. This triangular portion, the green area. Work by the spring then is equal to the base of the triangle multiplied by the height of the triangle divided by 2, which is 15 kilojoules.